Okay, let's talk about the oxygen dissociation curve. Some learning objectives. Draw a basic oxygen hemoglobin dissociation curve and identify the P50. You'll learn that. Identify and explain the clinical implications of the steep portion and flat portion of the oxyhemoglobin dissociation curve. You will learn that. And explain how changes in pH, PCO2, 2,3-DPG, and temperature affect the affinity of oxygen to hemoglobin. You'll learn that as well. So let's start with drawing a basic curve and identifying the P50. Before you do that, the first thing you need to learn, and frankly this is the most important concept, is that oxygen comes in two forms. Oxygen comes bound to hemoglobin. That is what's used for transport. The oxygen gets attached to hemoglobin in the lungs, goes to the heart, gets shot out of the heart to the rest of the body, and then is consumed. But when oxygen is bound to hemoglobin, it can't be used. It's just for transport. The other form of oxygen is when it's dissolved in the plasma as the pressure of oxygen. That is what's used to consume. So the whole part of the oxyhemoglobin dissociation curve is how much is bound to hemoglobin and how much is really being free in the plasma to be used. Both are equally important. Okay, let's draw the curve. You've got two axes. On the x-axis, you have PO2. On the y-axis, you have hemoglobin bound to oxygen, the oxygen saturation. And you've got this beautiful curve. Where does that sigmoid curve come from? Well, that is all about hemoglobin. Here's what you need to know about hemoglobin. Hemoglobin derives the oxygen dissociation curve's sigmoid shape. On the hemoglobin, there are 4 sites that oxygen binds to. And binding at the first site leads to conformational change of the remaining sites, leading to hemoglobin's increased affinity for oxygen. So after that first oxygen binds to it, well, hemoglobin becomes more sticky for oxygen. So let's start here. Let's identify the point representing blood entering the lung. Is it A, B, C, D, or E? I'll pause and let you think about it. Look at both the hemoglobin oxygen saturation percent on the Y curve and look at the PO2 on the X axis. The answer is C. Why is it C? Well, it's C because the partial pressure of oxygen in the pulmonary artery, that is when it's entering the lung, is about 40 millimeters of mercury. And that usually aligns to a saturation of about 80%. And you can see here, when you look down here, the partial pressure of oxygen is about 40. So that's one point on the curve that you can usually identify. How about let's go to another point on the curve that's even easier to identify. What is the point representing blood leaving the lungs? Is it A, B, C, D, or E? It's E. How do we know that? Because blood leaving the lungs in the pulmonary vein has a partial pressure of oxygen of about 100 millimeters of mercury, right here. And its saturation, if you're healthy, is almost 100%. Almost all of the hemoglobin is bound with oxygen, meaning 100% of the hemoglobin is saturated. So, a couple points. Here's one point where the blood is entering the lungs and the partial pressure of oxygen is about 40. Here's another point where blood is leaving the lungs and the partial pressure of oxygen is about 100 and 100% is saturated. So just to summarize, on this oxygen dissociation curve, or the oxyhemoglobin dissociation curve, we have this point up here, which is the pulmonary vein, where 100% of the hemoglobin is saturated. We have this point right here, where about 80% of the hemoglobin is saturated, and the partial pressure of oxygen is 40. What about this P50? What is P50? Well, P50 is not some magical number. P50 is simply the partial pressure of oxygen when 50% of the hemoglobin is saturated. I'll show you here, right here. Here's 50% of the hemoglobin is saturated. I go out here, and then I go down, and my P50 for this hemoglobin dissociation curve is what? It's about, I don't know, about 25 to 30. I'll do that again. P50 is the partial pressure of oxygen when 50% of the hemoglobin is saturated. Here is 50% of the hemoglobin is saturated. Over here, I drop straight down, and it's about 25 to 30 millimeters of mercury. So why is the P50 so important? Well, the P50 is used as a shortcut to describe the relative oxygen affinity based on an oxygen dissociation curve, meaning the P50 goes to the left and goes to the right, depending on whether the oxygen has a higher affinity or a lower affinity to hemoglobin, which is what we're going to get into soon. Again, to summarize, the oxyhemoglobin dissociation curve, here we have on the y-axis hemoglobin bound to oxygen. What percent is that? It goes from 0 to 100. When it's 100% bound, you're usually in the pulmonary vein. Over here, we have the partial pressure of oxygen in millimeters of mercury. And remember, the P50 is where 50% of the hemoglobin is bound, and it's referred to in millimeters of mercury. So here it's about 25 to 30 millimeters of mercury. And it has this sigmoid shape. And that's really interesting because there's a steep portion and a flat portion, which is what we're going to talk about next. So let's identify and explain the clinical implications of the steep portion and flat portion of the oxyhemoglobin dissociation curve. The underlying feature of the flat portion of the oxygen hemoglobin dissociation curve is that the flat portion promotes transport of oxygen from the lung. Let's dig into that. Here's the flat portion. Couple key points. Oxygen bound to hemoglobin is essential to transport. As PO2 increases from 40 to about 60, oxygen is just packed onto hemoglobin. And when it leaves the lung, blood has the highest content of oxygen possible. And then the hemoglobin remains packed with oxygen while it's traveling through the arterial bloodstream. So at first, I said that the flat portion is important. But then I mentioned that, well, from here to here, oxygen just gets packed onto the hemoglobin. So what about this little thing right here? Well, while that flat portion is so important, is that between about 60 millimeters of mercury and 100 millimeters of mercury, and actually even higher all the way over here. So we've been talking about how oxygen gets more bound to hemoglobin as the partial pressure increases from 40 to 60 to 100. What about when it goes in the opposite direction? What happens when it goes from 100 to 60? Well, because of the flat portion of the curve, it remains bound to hemoglobin. Because of the flat portion of the curve between 60 and 100, or between 60 and 360, oxygen remains bound to hemoglobin. And that's important because you want the oxygen to remain bound to hemoglobin as it travels through the body until it reaches a tissue where it needs to be consumed. That flat portion is the buffer zone. Now let's talk about the steep portion. Well, in the steep portion, which is right there, it allows for oxygen delivery to the tissues. Because remember, hemoglobin and oxygen bound together does not allow for consumption of oxygen at all. The only way that oxygen can be consumed is if it's dissolved in plasma. So, dissolved O2 is essential for aerobic metabolism. And tiny drops in the PO2 when PO2 is below 60 leads to a great increase in dissolved oxygen, meaning more oxygen to be consumed. So when you go from here to here, you see a huge drop off of oxygen bound to hemoglobin, meaning more of it is allowed to be dissolved in plasma and then used by the tissues in consumption. Let's move on to the next learning objective. Explain how changes in pH, PCO2, 2,3-DPG, and temperature affect the affinity of oxygen to hemoglobin. Remember the P50. That is the marker that tells us whether oxygen has a higher affinity or a lower affinity to hemoglobin. Here on this oxyhemoglobin dissociation curve, the P50 is about 30. But then all of a sudden, I move it over to the right, and the P50 is about 35. What that tells me is that here, hemoglobin and oxygen on this curve have less affinity for each other than they did before, because it requires a partial pressure of oxygen of 35 to achieve 50% of hemoglobin being saturated. So what parts of the body would you want to have a lower affinity of oxygen for hemoglobin? Well, you'd want to have it in places where you need to use the oxygen in aerobic metabolism. Places like your muscles. You can imagine that your muscles are hot, have a lower pH and a higher PCO2 because they're in aerobic metabolism. And this literally happens, that the oxygen dissociation curve is altered in the muscles based on local factors. The temperature, the pH, and the PCO2. We'll talk about the 2,3-DPG in a little bit. And at this P50, where the P50 is about 35 millimeters of mercury, more oxygen is free to float around and be consumed. Alternatively, what about where you have hemoglobin which has a higher affinity for oxygen? Where would you want to have oxygen more likely to clomp on, to stick to hemoglobin? Well, I'd want that in the lungs, because that's where you really sort of acquire oxygen. What are the lungs like? Well, the lungs are colder than the rest of your body because they're exposed to room air. They're more alkalotic. They have a higher pH and they have a low PCO2. And of course, you'd want that in the lung, because you want in the lung for oxygen to bind to hemoglobin so it can then be transported back to the rest of the body. So to me, this makes intuitive sense, even if the graph is sort of weird and difficult to follow along with. Where in the body things are hot, acidic, and have a high PCO2, you have a hemoglobin dissociation curve that has less affinity to oxygen, meaning more oxygen is available to be consumed. And alternatively, areas of the body that are cold and alkalotic and have a low PCO2, where you want oxygen to be bound to hemoglobin, you have a higher affinity along the oxygen dissociation curve. So what about 2,3-DPG? It's this weird thing. It's produced by the red blood cells. It increases production in settings of hypoxia, specifically altitude, but it takes a while to kick into gear. It doesn't happen right away. It takes about 7 days or so. In a lot of ways, 2,3-DPG decreases hemoglobin affinity to oxygen, similar to exercise. And you could imagine, if you're living at altitudes like we are, you're going to have overall a lower partial pressure of oxygen, and you're going to need to have it slightly less bound to hemoglobin so you can have more to consume. But again, it takes about a week to really kick into gear. And with that, let's review the learning objectives. Hopefully you can draw a basic oxyhemoglobin dissociation curve and identify the P50. Remember, it's a sigmoid curve based on the affinity of oxygen to hemoglobin. P50 is the partial pressure of oxygen, where 50% of the hemoglobin is bound. You can explain the steep portion and the flat portion of the curve. And you can explain how changes in pH, PCO2, temperature, and 2,3-DPG affect affinity of oxygen. And with that,